Sorry guys, I got cut off. I guess there wasn't enough space or whatever, but I think we finished this one. But remember, in order to do number 7 and 8, we need to remember the fact that the limit as x approaches 0 of sine theta over theta equals 1. And so you want to manipulate these guys so they look like this. So if I have 5 theta, I'm going to let this equal sine of 5 theta over 5 theta. But since there's really a 4 in the denominator, I'm going to multiply this by 5 over 4 so that this expression is equivalent to this expression, right? Don't the 5's cancel, and then I'm left with 4 theta in the denominator. And so the limit of this is 1. The limit of this is just 5 over 4, and so my answer is 5 over 4. Same thing in here. I'll rewrite this as sine 7 theta over 7 theta times 7 over 1, because really these 7's cancel, and so this expression is equivalent to this expression. And so this guy is 1 times this guy is 7, so the answer is just 7. Number 9, we're looking for the limit as x approaches 1 from the positive side of the absolute value of x minus 6 over x minus 6. Remember what absolute value by definition means. By definition, but really we can just do a shortcut here. I can just plug in 1. 1 minus 6, right? If I plug in 1, 1 minus 6 is negative 5, and the absolute value of negative 5 is 5, over 1 minus 6 is negative 5, and 5 over negative 5 is just equal to negative 1. So in exact cases like this, I can just plug in. But by definition, this is what's happening here. Right? It equals the positive when x is greater or equal to 6. It's the negative of this when x is less than 6. Since we're approaching 1, 1 is less than 6. And even though it's from the right, even 2 and 3 is again less than 6. So this is the guy we plug in over x minus 6. These cancel, and it equals negative 1. But just plug in. When we're approaching some constant, just plug in. Right, so negative 1 to the 6 gives me positive 1, minus negative 1 cubed times 4 is negative 4. Negative and a negative, we add, and so it's 5. Remember, there's no calculator, so make sure you remember how to do this. Number 11. Number 11, technically we can take a shortcut here. I know when we see this, we automatically want to do the conjugate. So if you go ahead and do that, you'll get this. And if you try to plug in 0 here, you get 0 in the denominator. So the conjugate did not work. Well, it didn't work because if I originally plug in 0, I get 2 plus 0 is 2. Square root of 2 minus 2 is not 0. It's some number, right? Some negative number over 0. So this does not equal 0 over 0. It's not indeterminate form, so I don't have to do anything more. I can go ahead and say does not exist. Number 12, as x approaches negative infinity of some rational function, that's when I look at my top heavy, bottom heavy. So on the numerator, I have x to the 5th over x squared. That reduces to x cubed. This is what x cubed looks like. We're approaching negative infinity, so to the left, I'm going down to negative infinity. 13, which of the following statements are true? So here's my piecewise function. Does f of 0 exist? Well, yes, it's 1, right? When x equals 0, my output is 1. Doesn't exist here, but here it does, so yes, for my function it exists. The limit as x approaches 0, does that exist? This one is definitely tricky. You need to know something about rational functions so that you can graph this and see what's happening. Well, so I'm looking as it approaches 0, because here it's definitely 1. But what's going on over here? So I factored it. I know at positive 1 I have a vertical asymptote. And for rational functions, when I have a vertical asymptote, I know there's a piece on the right and a piece on the left. and this piece on the left, look at this. From the right, as I approach 0, it's some height. From the left, as I approach 0, it's the same height. So, yes, the limit exists. But is it continuous? Well, no, because it's not defined at 0 here. So this is a hole. But this piece, when x is 0, is 1. It's up here. So there's a hole here. There's a removable discontinuity right here. So it's not continuous. And so 1 and 2 are the only true ones. Number 14, if f of x is undefined at x equals c, then the limit of f of x as x approaches c does not exist. Is that true? Well, I know I can have a line with a hole in it. If I have a line with a hole in it, let's say the hole is at c, well, then there's a hole here, so f of x is undefined, right? So this part, it's undefined. This part is true. But I know from the left, I'm approaching this height, and from the right, I'm approaching the same height, whatever f of c is, and so the limit does exist. It does exist, and so this statement is false, right? At x